confusion. My name is Manuel Sardinha. I'm very glad to be here. This is actually kind of a closure for me. The title of my presentation is the ironing process influence on the warping of ABS parts produced by fused filament fabrication. But I'm a PhD student. My PhD will not be really focused on this. It will be about thermoplastics polyurethane materials produced by fused filament fabrication. So this was the idea I had like 2 years ago, more or less, applying the ironing process in fused filament parts. So I did the first experimental test, but since then a master's student is now working on the final results. I hope I have the chance to show on this presentation. And so actually I will not only talk about the warping of ABS parts and its influence with ironing, but a brief overview of what we did with the ironing process on fused filament fabricated parts. So I guess the introduction is what we are doing now. Then I will try to explain briefly what is this ironing process, and then what we have already done and some of the results we published, the really effect of the ironing process on the warping of these parts, even though results are still coming in, and then some final remarks. I come from the University of Lisbon. The faculty is the Instituto Superior Técnico, and I'm a PhD student. I work in the Laboratory for Product Development. I guess if you are catching a flight back home, if you pass by Lisbon, I advise you take 1 or 2 days. It's a very nice city. So I will not explain you how fused filament fabrication work or FDM. I guess it depends how fan you are of the Stratasis company, but this is a scheme that really summarizes a lot of the thermal effects that will cause, in fact, the warping of these FDM parts. But here are probably the motivation of some of the results I will show you, some of the drawbacks that we commonly associate with this type of parts, which is low surface finishing, the strength of its parts, generally speaking, and most specifically to ABS or nylon or some specific materials warping effect. So what is this process we call ironing? So ironing was first devised to smoothen the top layers of FDM parts, mostly to serve as a visual smoother, as a visual effect. Okay. What you do is you scan the top layer of a part with your nozzle without extruding or extruding a very small amount of material. This is a well-known, for people who know what is ironing, a well-known YouTube tutorial that explains this just for you to see. This was the initial concept of the ironing process. So in fact, if I remember correctly, I hope I'm not mistaken, the slicer Ultimaker Cura was the first one to present us with this possibility of applying the ironing for top layers. It was around 2018, I guess. This is a screenshot of today. Today you can already implement ironing with a couple of more possibilities. What you can do is add a bit of flow and change the path. You do this scanning of the layer. What we did, my original idea was, what if we use this to scan not only the top parts of top layers of parts, but within the build process. So we created a Python script, and what we do is we grab the slicing, the G-code file that's going to be read by the machine, and we analyze its all the layers, and we can define when we want to apply ironing along the build process, in which layer we want to apply the ironing, in what type of path is the scanning going to happen, the amount of material, the cooling, the temperature, and so on. Yeah, since then, and again I hope I'm not mistaken, but again another very commonly slicer already has some considerations on ironing. This is a José slicer. But so, the first thing we did, this is already published a couple of years ago. Firstly, we just wanted to confirm, just to grasp a bit of better understanding of the ironing process as well, just confirm that when you apply these to top layers, you actually are reducing surface roughness. We tested a lot of samples. We also tested this for influence of size effect and so on, but we did not notice any influence of size effect. So we ended up testing a lot of very small cubic specimens, varying the raster of scanning, not the raster of deposition of the layer, and flow, no flow. This is a bit of the methodology and materials we used to scan. And in fact, we were able to reduce, we tested a lot of parameters regarding the ironing. This is the best result we achieved, okay? It was a reduction of about 60% in terms of surface roughness. But in fact, with almost all of the parameters we tested, or actually all, you can see a reduction in surface roughness on top layers, okay? Then what we did here, and I must say this is not the most intelligent of the ideas we have, but we then built prismatic samples and we applied ironing evenly across multiple layers, non-evenly, also a lot of different parameters to test the interlayer strength of these parts. And again, this is not the most brilliant idea. Why? Because these were samples subjected to 3-point bending. And so the weakest link in this low case scenario will be among the layers. And that's where we were applying the ironing process. So we would very difficult to have any improving properties here, but this is just to show you some of the things you can find or encounter when you try to apply the ironing process. One of the parameters is the inset, which is one of the distance between the outer perimeter of your part and the inside of your part. And so this is, I selected this picture specifically to show you, because here we can visually see it. We tested a lot of different things, and even if visually we cannot see it, we'd end up almost always creating some sort of stress concentration location, okay? So, but this is a nice example I would like to tell you, which is, in fact, we have a patented manufacturing extrusion technique based on FDM, which is a modular independent extrusion. And when you have multiple extrusions working at the same time, you will inevitably have seams, which are where the multiple extrusions connect. And so these, we have published a lot about this, these seams or these connection areas act in parts as a fragility. It's where most likely your part will fail. So what we did was we tested a lot of different seam overlaps and so on, but I guess we did a lot of test samples with different strategies. First thing we know, and then basically we applied the ironing in this seam location, okay? The first thing we noticed, as expected, is that the deformation of ironed areas and non-ironed areas is different, and also the location of fracture also varies. Contrary to if you don't have ironing, it will always break and have a very clear fracture location. And so this was the first thing we noticed, but an interesting summary, I guess, is that so in blue you have a normal specimen produced by one extrusion module, and then if you have two extrusion modules and you simply do it like the minimum overlap, even if there is necessary an overlap or you wouldn't have a specimen, you end up with what I was saying, a type of brittle fracture. So that's a fragility of your specimen. If you apply a type of overlap between in each layer, so in each layer, each module is extruding more an area, you start to have a type of plastic zone. But if you have that overlap with the ironing, and we are talking about a 1 millimeter width of ironing in this seam location, you start to increase this plastic area of your specimens. So related to ironing, to warping, so that was what we already more or less did. Not everything is published, but very different types of setups related with ironing. Related with warping, which is what the master student is currently doing, José, we are trying to address the warping of ABS parts. I forgot to mention, everything was related with ABS except the last one, the multiple extrusion, that was PLA. And everything was also done using Ultimaker. Ultimaker S5, if I am not mistaken, all of them, except the last one, which is our proprietary machines. And so here we are mostly dealing with curling, okay, which is the most common. I guess I'm running a bit late, but so what we did, again, a lot of different samples we tested, and then the first problem is have a reliable, repetitive warping of your specimen. So when you act upon it, you can measure how much did you reduce this warping effect. And here starts the problem. So this is what most of the things we are trying. So basically doing a ironing in the first layer, ironing the second layer, or ironing the third. Then the second thing is, what if we iron all three layers? What happens? What if we iron evenly across the height of the specimen? And so, at a first glance, this might look like kind of good results, but I struggled with this, and as I said, results are still coming in for this part, which will be a master thesis. And so here we can clearly see a reduction of the warping, the relative warping, but the problem is that repetitive, reliable benchmark. Because as you see, we are always comparing this to a different benchmark. This is why we went further back when we started doing this, and we spent a lot of time developing a type of protocol to have a consistent, so cleaning a printing bed, applying a specific adhesion and so on, specific temperatures. And so at first, I think these are good results, but one has to be careful because they are not compared all with the same benchmark. So this applying ironing the first, the second, or the third, as yes, we are more or less sure that it will help improving the warping or reduce the warping. All other strategies are, I believe, are failing. Here, if we just compare it even with this one, therefore, if we compare it with the same benchmark, even then we have a reduction of the warping. This is just to show you that very tricky. You can still reduce warping, but you can be causing all different types of other defects. And this is the base plate of this specimen, which applied 3 consecutive ironing layers in the first 3 layers of the build process, and basically you have over adhesion of your part, which is then very difficult to address. This is a qualitative analysis just to tell you exactly that even if you improve all other aspects of your process, you will have problems. This is just to reinforce that even if results are still coming in from the master thesis, I did but these are with very few samples, but I did this when we published our first research, And in fact, we already were proposing that this has a good reduction of the warping effect in ABS produced parts. Okay, so even if the results from the master thesis are still being analyzed, we are confident that that will work. So just to sum up, we effectively see that ironing can reduce surface roughness, at least on top layers. One of our future steps we are proposing, another master thesis, is to develop a device to apply lateral ironing. Okay. Also, the mechanical properties of these specimens that I believe are not very commonly used, but produced with multiple extrusion modules, has a high potential to increase these mechanical properties with either ironing or something related with this. So we are promoting a localized remelting of our specimens. Regarding warping, we still have to be careful and further studies are needed, but we are confident that at least in the first two layers it will have a positive impact. And that's it. If anyone wants to discuss something, I'm gladly here. Thank you.
Thank you very much.
I hope I did not use my time.
No, it's okay. Okay, we have time. Any questions? Yes?
Let me go again.
Yeah.
I understood from the initial talk, your initial part of the talk, that ironing reduces the stress concentration by flattening the surface. Okay. I can't see why is that related to the residual stresses and warpage.
Okay.
Are you annealing at the same time?
I'm not sure, because we are now applying a thermal camera to it, and we are not sure if we are doing a type of annealing. I think so.
Yeah.
Okay? Because what we are doing, we deposit the layer, okay, and then we are scanning it at a high temperature again. But this temperature is slightly below our test. Our test is slightly below the extrusion temperature. Okay, so we are promoting a type of remelting, a localized remelting of the layer, but we are not still sure what is really happening on a chemistry level over there. What we propose is that this is a mechanical process, and so one of the next steps I am proposing to a master student is, in the first layer you create a very small air pocket or void, and you use ironing as a directional contraction thing. So not as much as regarding the thermal stresses, because those will always be present, but mechanically you direct where material is going to contract, because you have a very small air pocket or multiple air pockets that still has to be focused. Did I address your question?
Okay. More questions? No? Okay, maybe one from my side. Can you quantify how much you can improve the surface roughness? Because I don't know if you can get very smooth surfaces or I don't know how much.
You can clearly quantify, I guess. So this is a non-iron top layer, okay, even though this is a very, very small section, you cannot see it, but it's 200 microns, okay, but we did multiple sections of a 10 by 10 by 10 millimeter cube, and then applying ironing with multiple strategies, and you clearly see a reduction in surface roughness all across the specimen, except for the outer perimeter, where it's very difficult to be exactly aligned with the normal contour of a part. This is the most tricky part of this process, I guess.
So you are talking about, 10 microns or 9 microns?
See here, yes. Here, which is in line with the best.
Lower than
this.
0.1 microns, for example.
How much, sorry?
0.1.
lower than this, it's hard to find without any other post-processing technique. Lower than this, naturally, I believe it's difficult to find. Maybe someone here
I
might disagree.
wondering if it can replace like machining, post-processing.
Yeah, the idea was that, but with the other post-processings, I think you can get a little below this. Okay.
Okay. Thanks again.
Thank you.